So today I'm going to present a new compiler, CRTC, that achieves low-cost privilege separation with compile time compartmentalization for embedded systems. So embedded systems. Embedded systems are everywhere. Your smartwatch, smart washing machine, even your traditional personal computer constitute of many embedded systems. So it would be wrong to say that embedded systems constitute the modern computing framework. But the problem is that these systems are very low power systems and they have really low processing power. So that's why people often sacrifice security in terms of performance. And we'll see in a bit what I mean by that. So in embedded systems, the software that's running on the embedded system is called a firmware. It might have threads, it might have different drivers, and it might also have a kernel component. Now, because I said that these are low power systems and people want to get the best bang for their buck. So as Atri said, that privilege separation or doing context switches is very expensive. So what embedded system developers do is that instead of putting everything in different modes, they put everything in the same privilege mode. So everything is running in the same privilege mode, even though logically we have different components in the system. In reality, everything is able to access everything in the system. Now you can already see why that's bad, right? If you have a vulnerability in one of the system, it can easily propagate to other things in the system, and it should be really trivial to take over the whole framework. So any guesses what's the solution we're going to propose? Compartmentalization. So compartmentalization divides the firmware into multiple components with dedicated resources called compartments. And at runtime, these compartments are isolated from each other. So usually compartmentalization frameworks, they work in two phases. First of all, they get the firmware, translates into a program dependency graph. If you're not familiar with program dependency graph, it's like a control flow graph, but on top of control dependencies, it also has data dependencies in it. The first phase is identification. In identification, they basically partition the program dependency graph and spit out a partition program dependency graph, where each partition is basically a compartment. The next phase is the enforcement phase, where every compartment is isolated from the other compartment. So our solution is called CRTC, or Comparted Real-Time C. And we have made the solution with embedded systems in mind. Low computation power, and everything is running in the same privilege mode. So Comparted C is a privilege-aware program language that achieves compile-time compartmentalization using program analysis. And to see how it works, I'll consider a toy firmware, where each node, it could be a data node, it could be a device node, and it could be a code node. And you can get the code recording from the slide. So as I said, the first thing that we need to do is identification. If you remember, the firmware already has the logical paths for different compartments. So we just use the privilege as the guiding principle for CRTC in compartment identification. And we discover all the threads in the system using thread discovery, all of the devices in the system using MMIO discovery, and anything else that's left out, we regard it as the kernel compartment. So at this point, we have recovered all of the logical components in the firmware. Next, we need to do enforcement, so they are isolated from each other. Again, this isolation should be low overhead, and we have to do it in the same privilege mode. So to do this, we provide specialized language dialects for each identified compartment. Each language dialect basically means that it's a special language or a language with a different programming expressivity. So in our work, we have three different types of compartments: kernel compartment, thread compartment, and the driver compartment. So let's just talk about each of the dialect in the system. The kernel dialect is the highest privilege. You can do whatever you want in this dialect. But it still has one restriction. The kernel compartment cannot directly access MMIO. And the reason it cannot directly access MMIO is the way we do our identification. Because anything that's doing MMIO is already regarded as the driver compartment. All right, now directly jump to the thread dialect, which is the least privileged compartment dialect in our system. So in the thread dialect, we have a lot of restrictions. The thread compartment cannot directly access MMIO. again, because of the MMO discovery, if we see there's a thread that is directly accessing MMO, we just throw an error, and the user has to like fix that error. Because of that, after that, all of those dependencies will go away. Next restriction, that the thread compartment should be memory safe. So to this end, we ensure that the code in thread compartment is type safe and memory safe, and we use checkc and the 3C tool to automatically convert all of the legacy code into safe code. And then we get memory safety. Next, we also ensure that each thread only accesses its own resources. So for this end, we conduct a couple of analyses. For static resources, we conduct a forward program slicing analysis. We conduct a field-sensitive, context-sensitive interprocedural alias analysis. And for dynamic objects, we conduct runtime object tracking. So after this step, we just get rid of all the dependencies between different threads. Let's call this analysis inter-thread isolation analysis, because I'm going to use this analysis again and again in the future. And lastly, similar to the inter-thread isolation analysis, we also do inter-thread kernel isolation analysis, and we make sure that the thread cannot access anything from the kernel compartment. All right, last dialect is the driver dialect. So in the driver dialect, we again ensure that the driver compartment should be memory safe. Same technique, checkc, 3C tool. Next, we ensure that the driver compartment cannot access kernel objects. Similar technique, inter-kernel isolation. And next, we also ensure that each device driver should access its own resources. To do this, we need to figure out where all of the devices lie in the firmware. So for that, we use the system view descriptor files, which are kind of like the device tree files for the embedded systems. We figure out where every device is in the memory layout. And next, we need to figure out what each MMIO pointer points to. For this end, like we have already discovered all of the MMIO pointers, but we don't know where they point to. We do a points to analysis and a value range analysis to figure out what each MMIO pointer is pointing to. And after that, we have different compartments that are isolated from each other. But that's not a real firmware. Because if anyone has worked with any firmware, they know there should be a lot of interaction between these compartments. So right now, if you try to do any cross-compartment access, because of our analysis and different type systems in our system, it will just like disallow the direct access. So to allow cross-compartment interaction, we could provide something called a compatibility layer. Compatibility layer is a kind of a higher privilege thing where you can think of it as a gateway. It's aware of all of the compartments in the system. And everyone can talk to this. And this compatibility layer can also talk to the kernel after appropriate checking. Again, it's aware of all of the compartments in the system and can move resources appropriately. And now we have a working compartmentalized software or firmware. To implement CRTC, we used a couple of projects. We modified Clang for type safety and other stuff like that. We modified LLVM, where we do a lot of our analysis. We also modified checkc because we add some more restrictions or more type safety compared to like the vanilla checkc. And we check or we evaluate our implementation on 2 real-world RTOS, FreeRTOS and Zephyr. And the platform that we used was STM32F4. In our paper, we also have a security evaluation, and we show how we can like thwart different existing known vulnerabilities in the system. All right, as far as the runtime overhead is concerned, as I said, even though most of our checks are at compile time, we do incur some runtime overhead, especially for the instrumentation, for type safety and memory safety, and the object tracking that we do across the compatibility layer. Again, it depends on the application that you're using, but in general, for the evaluation that we did for our applications, we incurred an average overhead of 2.63%. As far as memory overhead is concerned, again, most of our memory overhead comes from our instrumentation and the metadata that we use for object tracking. And on average, we conduct an average overhead of 1.75%. With that, I would like to conclude my talk. we presented the CRTC. It's a new privilege-aware language with compartmentalization. It provides a fast isolation mechanism for embedded system, and we evaluated on real-world programs. And it's a really cool project because if you write your code in CRTC, it basically realizes what type of code you're writing. And if you want to like see how working with CRTC, it's kind of like working with Rust, but this compiler nags more than Rust compiler. All right, so with that, I'll take any questions you guys have.
All right, I'm going to take chair privileges again. I know some of you people know this stuff, so come up here and ask questions. It's like my intro to security class. Got to poke these people. OK, actually, so a lot of really cool work. Exciting. So I'm interested. You show object tracing was high. When you had it on your earlier slide, I was like, oh, they're doing object tracing. This would be interesting. Why is it high? Did you get to investigate it at all? Any insights on where the cost comes from?
Oh, the object tracking?
Yeah.
Oh, so basically, like it's like the overall overhead is kind of low. That's why even if you have like a little bit of object tracking, if you have any dynamic objects, it's gonna be like high whenever you have like sharing of dynamic objects between components. So it depends on the application.
How do you share? Do you use message passing, or do you actually do copies like marshalling?
So basically, the idea is that all of we didn't talk about the actual typing thing, but everything in the system has a separate type system. So whenever you want to like share something, you basically cast from one pointer to another pointer. But for dynamic objects, because you cannot figure out dynamic stuff at compile time, so you have to add some metadata to see where it's belonging to. So this is where the overhead comes in.
Awesome. Thank you so much.
I have one special question on the implementation part. As we know, like no matter in the Linux or in Zephyr or RTOS, the scheduling part, the interruption handling part, the timer part, and the memory management part, they are mostly implemented in assembly. So how could you apply the LLM tools and parse them from there? Yeah.
That's a very good question. And the problem is that if you realize the kernel compartment is kind of a big compartment right now, and it's the highest privileged compartment in our system. But right now, we just say because we trust the compartment, the kernel compartment, we do allow it to do that kind of stuff. But if you hold your question for one more talk, we'll talk about how we can.
He cheated. OK.
Thank you.
But no, that's a good question. So everyone remember that.
All right, well, let's go ahead and thank our speaker.